For white noise, the variance-covariance matrix has an especially simple form. It's just equal to some constant, which is sigma squared, the variance of an individual value, times this quantity, which is called the Kronecker delta. It's kind of like the Dirac delta function, except that for the Kronecker delta, it's non-zero only for a limited set of values, applies to the indexes, the subscripts. Delta sub jk is equal to the Dirac delta function of the difference between the index values. So it's 1 when j equals k, that is to say we're looking at the same index value. It's 0 when j is not equal to k. We can turn this set of equations into a single matrix equation by just writing Greek letter subscripts and thinking of it as a matrix. The symbol delta sub jk I'm using to denote a set of values which are 0 except when j equals k, but the symbol delta sub alpha beta I'm using to indicate a matrix, the whole thing, which happens to be equal to the identity matrix. For a stationary time series, the mean is constant. I'll call it some constant mu. The variance-covariance matrix is a symmetric Toeplitz matrix. So we can say that the expected value of the product of two quantities is their mean squared plus the variance-covariance matrix. Here it is in matrix form, which is the same except that we're just thinking of things as being vectors and matrices, which is why I've used the unit vector. Now, this serves to emphasize just how fundamental is the variance-covariance matrix. Now, data aren't always stationary. There are a lot of methods and models we can apply to a stationary time series, but if the time series is not stationary, those methods aren't going to apply. Sometimes, however, we can find a convenient way to make it so. For instance, the data in the following time series is not stationary, but it is still the result of a purely random noise process. We can make it stationary in this case and in many cases, even when there's a signal present, even when it's not just a random stochastic process. We can eliminate the drift, the changing mean value over time, by computing the first differenced time series. The first differences are just defined as, to get this first difference value, you take this value and subtract the previous value. This uppercase Greek letter delta is used to indicate the first difference operator. And it can be thought of as an operator, and it transforms a time series into its first differences. Now, if we have a time series process, that's fine. We've got first differences for all the values. But for an observed or a realization of a time series process, the first difference from the initial value is undefined because we don't know its predecessor. So in that case, the first difference time series has one fewer data point than the series from which it's derived. The first differences of the set of data we showed in the previous graph are shown here. And now we have a time series in which it is stationary. Do be aware that if a time series is the sum of signal and noise, so it's the sum of a deterministic part and a stochastic part, first differencing is going to affect both of those parts. It's going to affect the signal as well as the noise, and in some cases, it'll even eliminate it. Suppose, for instance, a time series is the sum of a perfectly linear trend and stationary noise, so that x values are intercept plus slope times time plus stationary noise. When we compute the first differences, we can get this. However, if the time series is evenly sampled, then the difference between consecutive times is going to be the same always. It's going to be some constant tau, I'll call it. And in that case, the first difference operator applied to the time series gives a constant, which is slope times time spacing, plus the first difference of a stationary process. Now, this happens to be a stationary noise process itself, but it's not a zero mean process because its mean value is beta 1 times tau, unless the slope was 0 to begin with, which wouldn't really make sense for this example. It's not white noise because it shows autocorrelation at lags other than 0. In particular, its lag 1 autocorrelation is going to be -1/2. But it is a pure noise process. There's no signal to extract because we have eliminated the signal by applying the first difference operator. Now, suppose the trend wasn't as simple as linear. Suppose it was a quadratic function of time. So that the data values are intercept plus linear coefficient times time plus quadratic coefficient times time squared plus a white noise process. Well, if we apply the first difference operator and again assume that the time spacing between consecutive values is always constant, equal to tau, we get this. This is a constant because it involves the time spacing tau. This is not a constant because it involves the time spacing tau and it involves the time. And we also have the first difference of the white noise process over here. So this is not yet stationary because a linear time trend, this term here, is still present. Well, we got rid of a linear time trend previously. Let's do the same. Let's apply the first difference operator again. That's going to give us this. This is constant because the time spacing is constant. And this is the first difference operator applied twice to a white noise process. Now we have a stationary time series to work with. The twice applied difference operator, written often as delta squared, is called the second difference operator. In general, the uppercase Greek letter delta is used to indicate the first difference operator. With an exponent, it means that operator raised to a power, which means apply it more than once. In general, a signal, which is a polynomial of degree p, will be eliminated by applying this difference operator p times. Now, in some fields, notably in economics, it's customary to remove trends by applying the difference operator enough times to make the data stationary. That's fine. It works. But in the physical sciences, it's usually the signal that we're more interested in. Removing it by repeated differencing eliminates exactly what we want to understand. One of the focal points of this particular course is not to rely on the viewpoint that differencing is always the way to deal with non-stationary time series. Sometimes it is, but in the physical sciences, it can sometimes be a counterproductive approach.